Greetings to all. My name is Amelia, and today my group, Group 8, will be presenting our presentation for PDP2. Our members consist of me, Amelia, Anis, Amir Arif, Fikri, and Mushira, and our supervisor is Dr. Noni. Greetings, my name is Amelia, and I will be presenting about the reaction design and network. According to the onion model, when designing a plant, we first start with the reactor. And then when we finalize on that, we will go to the other layers, which are separation and recycle, heat network, heat exchange network, and utilities. Greetings. This is the process of choosing the appropriate reactor for our process. Firstly, we considered solvent extraction. Second alternative was hydrotreating and hydrocracking. And then based on research for group 3 products, we have to use a more severe process such as hydrotreating and hydrocracking. However, since our feed is not that high in contaminants, it was decided that the hydrotreating unit can be removed. Upon finalizing on the type of reactors that we would want, the next step would be the arrangement of the reactors. So the first arrangement is as shown, where apart from between the reactors, there are separators. Or else the fifth alternative is to add a second hydrocracker in order to improve the viscosity index further. Lastly, this is our finalized design where the feed enters the first hydrocracker and then the second before going through a separator where recycled gas will be returned to the previous reactor, and the other feed would enter the next reactor, which is catalytic dewaxing, and subsequently hydrofinishing. However, before it reaches the column, it goes through another separator. And lastly, group 3 products can be obtained.
Assalamualaikum and hi. My name is Anis Raya and I will be presenting separation process. Basically, separation process is a method that converts mixture of liquid or chemical solution into two products or even more constituent products. In this plan design project, there are two types of separation process experienced in the system. First is the distillation column and the second one are separators. In distillation column, feed enters as liquid or mixture which contains wide range of hydrocarbons. Distillation column is placed to separate all mixture into light gases, naphtha, kerosene, diesel, and also base oil. On the other hand, separators are placed in the system to separate three different phases, which are oil, water, and also gas. These three way separator are very famous type of separator in the petroleum refinery. The purpose of the separation are to produce high efficiency product, to maximize separation, and also to minimize operating and maintenance costs.
Thank you, Anis, for the explanation about the separation process. Now, I will explain about PFD and PNID. This is our PFD after heat integration. This is in our base oil processing plant, we have four major equipment. The first one is hydrocracker reactor, hydrodewaxing reactor, hydrofinishing reactor, and lastly distillation column. The raw material need to react with this reactor in order to produce desired product. Lastly, it will separate at the distillation column before it will store at the storage tank. This is our piping and instrumentation drawing, PNID. PNID is a detailed drawing that shows all information needed. For example, it shows the control system inside our base oil processing plant. In our base oil processing plant, we have control strategy in order to prevent any incident from happening and also for safety precaution. For example, we have temperature controller in our heat exchanger, cascade controller at reactor, and lastly level controller in the separating vessel.
behavior of other devices or system using the control loop and to regulate a safe and efficient plant operation. The control system is consisting of few parts which are sensors, transmitter, controller, and finally a final control element. There are three types of process variable which are control variable, which is to quantify the performance or quality of the final product. Secondly is the manipulated variable which are adjusted to keep the control variable at their set point. And lastly is the disturbance variable which represents the input variable that can cause control variables to deviate from their respective set points. There are few classifications for control strategies. Firstly is the feedback control system, which output is controlled during its measurement as a feedback signal. The feedback signal is compared with the reference signal to generate an error signal, which is filtered by a controller to produce the system control input. There are two types of feedback, which are positive and negative feedback. Next is the feedforward system. It's a mechanism which prevents problems before they occur by monitoring the performance input and reacting to maintain an identified level. Lastly is the cascade control. It involves the use of two controllers, which the output of the first controller providing the set point for the second controller, which is the feedback loop for one controller nesting inside the reactor. The system is divided into three systems, which are 11 for hydrocracking, 12 for catalytic dewaxing, and 13 for hydrofinishing. For each equipment, the manipulated variables, control variables are specified to determine the process variable and set the control system. For Unit 11, there are a total of 50 equipment which is applied with the control system. For Unit 12 or catalytic dewaxing, there are 3 equipment that is controlled, but for Unit 13, there are over 9 equipment that is controlled. That is all for the control strategy. Now we talk about the hazard probability and probability or HAZOP. The objective for the HAZOP is to identify the hazard and the probability issues, analyze the existing safeguard, and lastly to provide the recommendation for the hazard identified. Next, there are few steps in correcting hazard. Firstly is to break into several process units from the detailed flow sheet. Second is to choose a study node and define its purpose and determine the process safe limit. Next is to pick a process parameter. Then we need to apply guide words to the process parameter to suggest the possible duration. Next, if duration is applicable, identify the possible cause. Then we have to evaluate the consequence of the deviation. And lastly, we can recommend the action to mitigate the deviation. Is the node that has been selected and the purpose for each the equipment. There are a total of 8 nodes that have been considered for the hazard study. The parameters for each equipment is also been set to identify for the duration. This is the hazard that had been done by a group. For each of the node, the parameter has been set, and different guide word has also been set for each the parameter. Some of the different guide word that can be used is no, less, more, reverse, as well as, and much more. The causes for each of the deviation has also been proposed, and the consequence for each deviation is identified. Then, the effective set guide has also been considered for each of the deviation. This is to ensure the severity of deviation and how the control action is being taken in the node. After the severity of the risk is identified, the hazard recommendation or safeguard will take into action to reduce and limit the risk from deviation.
Into the waste management, there are three types of waste generated by the plant, which are solid waste, liquid waste and gas emission waste. Solid waste come from the catalyst which used in the reactors. Solid catalyst contains metal, metal oxide, and even sulfides, which has been used in petroleum refinery to clean up fuels and other useful products. However, catalyst waste does not generated every day due to the catalyst span which lasts years. Next, liquid waste, which come from the separator unit, where it separates sour water from oil and also hydrogen recycled gas. Sour water is liquid form of hydrogen sulfide. Sour water is very dangerous to the environment and also human being. Hydrogen sulfide contains carcinogenic gases, which if the exposure is too long, it may cause someone to develop cancer. Not only that, just think about the environment, sour water is too acidic, hence if the sour water being discharged without proper treatment, a lot of aquatic organisms and also land experience bad impacts. Lastly is the gas emission. In this project, main gas emission is the flue gas where it comes from the furnace. Generally, flue gas composition is depends on the fuel gas used for burning. In this project, carbon dioxide has the highest composition among the others. Carbon dioxide is not a waste if the composition is not too much. However, in industrial scale, it is considered waste due to the excessive amount of carbon dioxide emit, which can cause greenhouse effect and global warming in the long run. So this is the identification of waste from the plant. As mentioned, solid catalyst waste is not considered a major waste since they're not being generated every day. Hence, tabulation of major waste, which are hydrogen sulfide and carbon dioxide gases, is done. However, hydrogen sulfide also has less composition, but since the type of waste is toxic and hazardous, it is considered a major waste.
I will proceed with law and regulation regarding gas waste. In Malaysia, we have Environmental Quality Regulation 1978, also known as Clean Air Regulation. This regulation limits the emission of any hazardous gas to prevent any source of pollution in the surrounding environment. For our gas-based oil processing plant, we have two types of waste that we generate, which is carbon dioxide and also nitrogen. But in clean air regulation, carbon dioxide and nitrogen not considered as pollutant. Thus, we have no waste that need to be treated or need to install any air pollution control. But somehow, we have a few hazardous gases in our processing plant that we need to look into to prevent any any gas emission to the environment.
Capital cost estimation used to estimate capital and operating costs for a chemical processing plant. Length factors are typically considered when calculating capital costs. While there are general length factors, which are for solids, fluid, and also mixed processes, it is recommended that the length factors being considered individually. Since our industry mainly processing fluid, values for fluid is taken. Total capital cost is a summation of fixed capital cost and working capital. Based on this table, we can conclude that the total capital cost for our plant is around RM 569 million.
Thank you, Mushira, for explaining about the waste treatment method. Next, I will be explaining the first part of the economic analysis, which is about the economic potential. Now, the economic potential can be broken down into three, which are firstly, that one, when we minus cost of raw material from the revenue. Secondly, when we into consideration the cost of utilities. And lastly, when we subtract all of that with the annualized cost of equipment. Now, for a plant to be considered financially viable, all three of the economic potentials should be positive. One of the main assumptions we use when calculating is that our plant operates for 350 days per year at a rate of 24 hours per day. This slide will show economic potential 1. Firstly, we calculate the total products in order to get the revenue. So based on values obtained from HISIS, the output are as shown. So apart from the main product, which is group 3 base oil, there are also other products that come from the fractionation column, such as naphtha, kerosene, and diesel, which can also be sold to get more revenue. Based on the calculation, our annual revenue would reach almost 5 billion ringgit per year. After that, we considered the cost of raw materials. Since the hydroprocessing process uses up a lot of hydrogen, that is one of our main raw materials, followed by the main feed that enters from the BDU, which would be obtained from a nearby refinery. Based on that, our total cost is around 3.7 billion ringgit per year. When we subtract the revenue from annual costs, we still get a positive output, which is around 1 billion per year. Next, we can calculate the next economic potentials. Firstly, in terms of utility, our plant would use up electricity as well as fuel for the furnace, which is our heating utility. Based on the calculation, our annual utility cost is approximately 76 million ringgit per year. When we subtract this from the previous EP1, we still get a positive output. Next, our final economic potential, we took into consideration the total cost of equipment, both major and minor, and the total cost came up to approximately 124 million ringgit. Again, when we subtract that from our EP2, we still get a positive output, which means that our plant is economically justifiable.
Now, I will talk about the catalytic devising reactor, which is R1201. The function of the reactor R1201 is to convert the structured hydrocarbon into branched compound or isomers through isomerization. This is to reduce the pour point of the stream and preventing it from crystallizing. There are few steps in the design methodology. Firstly is the selection of the major equipment. Next is the justification of the selected reactor. After choosing the reactor, we need to determine the optimum operating condition. Next is to gather the data from the high simulation. After that is to determine the volume from the space velocity. Then we can determine the size of the reactor. After that, we proceed with the mechanical design. After completing the mechanical design, we can calculate the cost. Then we proceed with the technical drawing and lastly do the standard operating procedure. Next, we will move to the reactor selection. There are many types of reactor that have been taken account into choosing the suitable reactor for the process. After considering the parameter, there are two types of catalytic reactor that has been chosen for the process, which are packed bed reactor and fluidized bed reactor. Each of the reactor has its own advantages and disadvantages. So the advantages of packed bed reactor are high conversion per weight of catalyst, low operating cost and low maintenance, can operate continuously, and little wear on catalyst and equipment. While for fluidized bed reactor, it has rapid mixing, high heat transfer, and also easy to do the regeneration process for the catalyst. Some of the disadvantages of packed bed reactor are less temperature gradient or undesirable thermal gradient may occur, inefficient heat exchange, and may be difficult to service and clean. While for the fluidized bed is high operating cost and maintenance cost, large reactor vessel size, and lastly, catalyst erosion. After considering its specification, packed bed reactor was used for this process. Next, I will go to the operating condition. The operating temperature and operating pressure were based on the high shift data and is the optimum temperature for the reaction to occur. It also does not affect the performance of the catalyst. The catalysts used for this process are zeolite or ZSM5. Next, I will go to the reactor sizing. Firstly, the volume of the bed is calculated by using this formula and the volume that we get is 53.46 meter cube. After considering the bed void fraction which is 0.4, we get the bed volume which is 74.85 meter cube. By using the cylinder volume formula, we can determine the diameter of the bed, which we get 3.08 meter. And by using the slenderness ratio, we can determine the length of the bed, which are 9.24 meter. And finally, we can get the reactor length by taking into account 10% free space at the top and the bottom for the support of the catalyst bed. And we get the reactor length, which is 10.17 meter. The reactor diameter is also determined by the slenderness ratio, and we get the value of 3.39 meter. Next, I will explain about the mechanical design. The design pressure is used based on the 10% safety factor and we take account for the operating pressure, while the temperature is 5% based on the operating temperature. The material chosen for this reactor is carbon steel. This because it has good temperature distribution properties and it also has lower cost compared to other types of material. The wall thickness has also been calculated and the value that we get is 223.52 mm. The internal diameter was based on the HISIS value and it was used to calculate the outer diameter and we got the value of 5146.86 mm. For the head and the bottom closure, the principal type used are torus spherical heads. For the minimum thickness, it was calculated and we get 223.52 mm. For the total height of the head, the straight face of the head cover was assumed to be 10 mm and the value that we got from the calculation are 1.001 meter. Next, I will proceed with the mechanical design. The vessel support that we use for the reactor is the skirt. For the flange, it functions as the second most used joining method after welding and is used when joints need dismantling. There are many types of principle used for the process industry and the one that we use for the unit is welding neck. Welding neck is used because it can withstand high pressure and temperature application. The flange was calculated and the thickness that we got is 433.28 mm. The minimum bolt area was also calculated and the value that we get is 1.21 meter squared. For the gasket, asbestos with suitable blinder for the operating condition is chosen. By taking account the gasket material parameter which is asbestos, the gasket inner and the outer diameter is calculated. The nozzle diameter was also calculated based on the formula. By using the inlet flow and the outlet flow of the respective density, we can get the nozzle diameter. And finally, the value that we get is 2662.35 mm for the inlet nozzle diameter while 2792.99 mm for the outlet diameter. And finally, the nozzle thickness was also calculated based on this formula. And taking into account the corrosion allowance of 2 mm, we get 132.69 mm for the nozzle thickness. Next, we move on to the specification sheet. After all the process design and the mechanical design has completed, the design and the values are tabulated in the specification sheet. This is so that it's easier to read the design and the specification of the equipment when it is tabulated. This is the technical drawing of the reactor R1201. The reactor is presented in the side view, top view for the inlet and outlet, and finally the catalyst bed dimensions. The drawing dimension is drawn based on the ratio of 1 cm to 0.2 meter. And finally, we go to the catalytic deviation reactor costing. The costing is being done based on the correlation method. The reactor diameter and height was calculated from the mechanical design. The material factor is considered based on the carbon steel value, which is 1. The pressure factor and also the correction factor was based on the operating condition and used in the cost calculation. Finally, we get the installation cost, which is $8,000 and $1,000 for the purchase cost. For the total cost, we get the $9,000. For the actual cost is calculated by multiplying with the current Malaysia ringgit price, which is 4 ringgit and 10 cents. And finally, we get the value of 3 million ringgit for the cost of the reactor. Okay, that's all from me. Thank you.
Assalamualaikum and hi. Thank you, Fikri. My name is Nur Musha bin Zulkifli and I will be presenting about hydrofinishing reactor R1301. For your information, this reactor helps to improve oxidation, thermal stability, and also the color of base oil by removing aromatics, polar compounds such as oxygenates, remaining sulfur, and also nitrogen. So the design methodology for this reactor is we will start first with reactor selection. After that, we will go to operating conditions from HYSYS, and then material of construction selection. After that, we will go to reactor mechanical design, equipment costing, specification datasheet, and lastly, technical drawing. For the reactor selection, fixed bed reactor has been compared to fluidized bed reactor, and it has been chosen due to the following reasons. Firstly, it has higher conversion of reactants. Not just that, less catalysts will be entering in the reactor. It also could save costs as the capital and maintenance costs are lower. Besides that, it uses lesser power consumption and there is no frequent catalyst regeneration. And these are the operating conditions. The inlet temperature is 398.1 degrees Celsius. The inlet pressure is 4,542 kPa. The catalyst used in this reaction is nickel molybdenum with aluminum oxide supported catalyst. The bed void fraction is 0.391 and the inlet flow rate is 225,275.44 kg per hour. Based on the operating conditions, suitable material of construction has been selected. For hydrofinishing reactor, I use stainless steel to construct as it has high tensile strength. It also does not corrode easily, thus require low maintenance. Most importantly, it is environmentally friendly, which will not cause pollution. Coming to the reactor height and length, to calculate the volume of reactor, the volume of bed must be known. Using the formula given, the volume of bed is 113.54 meter cube. Given the slenderness ratio is 3D equals to L, hence the volume of reactor is V equals to 3 over pi d cube. Knowing the diameter and length of bed, it is assumed that there is 10% free space at top and bottom for support. Therefore, the length of reactor is 12 meter and the diameter is 4 meter. Going deeper into mechanical design, the design pressure and temperature are operated at 5% higher than the working pressure and temperature for safety consideration. The wall thickness is determined by using the formula given and it is 95 mm. The head enclosure used for the reactor is ellipsoidal head since it is the most economical head which can work at a higher design pressure compared to toric spherical. The design stress is 105 Newton per millimeter square based on the design temperature. Welding efficiency is 1 as it is considered seamless, which means there is almost no gap between the weld and the joint. Corrosion allowance is 2 mm since stainless steel is used. Based on the formula, minimum head thickness that I get is 91 millimeter. This value is later used to know the outer diameter of reactor, which is 4190 millimeter. Assuming straight flange is 38 millimeter for ellipsoidal, we can get the reactor height including the head, which is 14.08 meter. Flange is the second most used joining method after welding, and it is used when joints need dismantling. There are many types of flange used in the process industries, and the one that is most commonly used is welding neck. Welding neck flange is used because it can withstand extreme operating conditions. The flange was calculated using the formula given, and the thickness that I got is around 801.5 millimeter. The minimum bolt area was also calculated, which is around 1.209 meter square. For the gasket material, corrugated metal asbestos inserted soft steel is chosen. Gasket inner and outer diameter are calculated, which are 4210 mm for inner diameter and 4981 mm for outer diameter respectively. The nozzle diameter was also calculated based on the formula. By using the inlet flow or outlet flow and the respective density, we can get the nozzle diameter. And finally, the value that we get is 196.27 millimeter for inlet nozzle diameter, while 197.04 millimeter for the outlet diameter. For the nozzle thickness, it was also calculated based on this formula and taking account the corrosion allowance of 2 millimeter for carbon steel, we get 95.94 millimeter for the nozzle thickness. For the reactor costing, it is based on the correlation method, which involves installation cost and purchase cost. The reactor inside diameter is 13.12 feet. The reactor height is 39.37 feet. The material factor is 2.4 because we use stainless steel, low grade. MNS is 1309.8. Pressure factor is 1.47. Correction factor is 5.292 by using the formula given. The installation cost, after we calculate, we got 1.125 million. The purchase cost is 797,249.18 dollar. The total cost is overall is 1,922,919.28 cent. After we convert it into RM, we got 7,918,581.27. This is the specification data sheet for hydrofinishing reactor R1301. It is basically a table that includes all the information on the reactor in one table. This is to make it easy for the readers to read because all the information are gathered in one place. Lastly, this is a technical drawing of reactor R1301. The reactor is presented in the side view, top view for the inlet and outlet nozzle, and finally the catalyst bed dimensions. That is all from me. Thank you. In order to treat hydrogen sulfide gas, a method of treatment used is by using saltwater stripper. In saltwater stripping, there are two main processes, which are degasification and acid gas stripping. For degasification, saltwater from feed stream is cooled and fed to a degasser or flash drum to remove dissolved hydrogen, methane, and other light hydrocarbons that are known as salt gas and is sent to sulfur recovery unit (SRU). Degassed water is later pumped into a surge tank, which aids the removal of entrained liquid hydrocarbons and solid particles present in the sour water. The next step is acid gas stripping, in which the degassed water is heated in feed bottom exchanger before being fed into hydrogen sulfide stripper column. Steam is injected to heat the sour water and strip the hydrogen sulfide overhead. Steam generated can be either external steam, steam generated by a reboiler, or hot hydrocarbon stripping vapor. After that, the stripped water is cooled back in the feed bottom exchanger for use to generate steam or treating, while hydrogen sulfide gas removed is cooled in a pump around cooler or condenser and is later sent to SRU for further treatment.
I will explaining my major equipment which is furnace. Before I proceed any further, we need to know what is the function of the furnace. Furnace F1101 is used to increase the material temperature to a desired temperature before it entering the first hydrocracker. This is my design methodology that I use to design my major equipment. First, I select the major equipment, which is the furnace, select types of furnace that I need to design, gather all the data from the simulation HYSYS, determine the number of tubes from the heat duty, calculate the dimension of the furnace. Next, I'll proceed with the furnace mechanical design, equipment cost analysis, draw the technical drawing, and lastly, I will come up with the standard operating procedure. These are the types of furnace that are available in the chemical processing plant. First, we have box heater with a bow coil, cylindrical heater with helical coil, cabin heater with horizontal tube coil, box heater with vertical tube coil, cylindrical heater with vertical coil, box heater with horizontal tube coil. For the furnace selection, I'll select type E cylindrical heater with vertical coil because of a few reasons. First of all, it is simple to design because of the cylindrical shape. It also proven to save some space compared to the other furnace. It's less expensive and it's flexible as the convection part of the furnace can be installed, can also include in the design or not. These are the operating conditions for my furnace F1101. We have the parameters of vapor, temperature, pressure, molar flow, mass flow, liquid flow, and so on. These values are for the inlet, outlet, air, and also flue gas. For the calculation part, I show the calculation for the radiation section. For the radiation section, it is shown that 70% of the heat comes from the radiation section. So we need to calculate the area of the radiation section. From the PTS Petronas Technical Standard, it mentioned that for the radiation part, the heat flux cannot more than 47.7 kilowatt per meter squared. So we have the flux and also we have the heat duty. We can calculate the area of the radiation section, which is 250 and 88.208 meter square. For mechanical design, I show the sample calculation for designing step. We assume the pressure drop which is 60 Pascal. These are the formula for the pressure drop. So we have constancy operating at atmospheric pressure. So we can calculate the height from the formula. We assume the outside temperature is 35 degrees Celsius and the inside inlet temperature. So the equation of the top part is the calculation to get the height of the stack. So in the PTS as well, Petrotechnical Standard, it mentioned that minimum stack of height must have 5% bigger from the calculated height. This is for the safety precaution. So we have our stack height, which is 8.1809 meter. Mechanical design for sizing of convection site. We need to calculate the dimension of the convection site, which is the length and the width of the convection site. We have the tube diameter, space between the tubes, number of horizontal tube, and also number of vertical tubes. So our total tube is 19 tube, and we also included with the insulation thickness, which is 0.1 meter. So we plug into the equation, and we have the convection height, which is 2.99 meter, and the width of the convection site, which is 2.79 meter. After the completion of gathering data from HYSYS, assumption, and calculation, we have come up with the furnace specification and furnace design for furnace F1101. We have tabulated all the data in the specification sheet. The reason why we have to do the specification sheet is because it is easier to refer for the design mechanism and also the design dimension. So we have no problem to refer to the design. This is furnace F1101 technical drawing. So for this drawing, we have the view from the cross-section view from the side, from the top of radiation side, and also the top of the convection side. So this technical drawing specify the dimension of each part of the view, such as the thickness, the distance between burner and the wall, and many more. Costing for furnace F1101. The types of furnace that we design is cylindrical vertical tube. In order to get the cost, we need to use this equation. All the parameters that needed are tabulated in the table. The heat duty is the weightage for the cost. So we plug in all the information to the equation and we get the cost in 2010. So we need to use the index to get the current cost. So the total cost for furnace F11 is 3,825,833.56.
As for major equipment, I have done the equipment design for distillation column. Firstly, I would like to explain on the design methodology, which involve two stages. First is the process design and the second is the mechanical design. In process design, I have done the determination of operating procedures, selection of type of contacting device, determination of stage and reflux requirements, column sizing, and column internal design. While for mechanical design, I have done the vessel, internal fittings, vessel supports, nozzle, technical drawing, and also the specification sheet. There are two types of column being considered, which are batch distillation column and continuous distillation column. However, after several operating conditions are taken into considerations, continuous distillation column is chosen due to the higher efficiency, facilitate multi-stages separation via side stream, and much preferred for petroleum distillation. In designing multiple component distillation, the column design may done by determining the heavy key and the light key. Heavy key is a pseudo component 4 and the light key is a pseudo component 2. By assuming ideal condition, relative volatilities can be calculated based on the equation shown, which is the alpha equal to Ki over Kj. The R actual is actually 1.3043 and the N actual is 28 stages. Number 4, we need to identify the feed point location by using the empirical correlation by Kirkbride. Then the feed location is at tray number 20 from the top of the column.